Hello class, this is Professor Ardo calling in here to give you a video web demonstration of some of the crystalline packing that we talked about in class, I don't know, about a week ago. Obviously we're on to solutions now, but I figured for this fantastic President's Day holiday, I would give you a special review mini lecture on the crystalline packing. I'm calling in right now from Cancun, Mexico. I decided to leave the country for President's Day. It just seemed fitting. No, I actually am in Cancun, but I'm here for a conference. So I'm in my hotel room trying to show you this. So I brought some things with me. Let me show you here. Okay, some of these models all the way to Mexico. And so what I want to do is I want to just flash back. I'm going to have to jump between the slides so I can tell you what slides to look at. If you open the slides and you look at slide 24, I showed you that in 2 dimensions, when you pack 2-dimensional hypothetical atoms as closely as you can, you'd pack them hexagonally. Why would you do that? Because you'd maximize the intermolecular forces. And we know that that's what materials want to do. They want to maximize their intermolecular forces, at least in the absence of entropy. That is the driving force for forming different species. So when you pack these in 2 dimensions, you pack hexagonal. And you can see that you end up with this little rhombus-like shape on slide 24. That's just showing you a 2-dimensional unit cell of packing hexagonal. Now, if you jump back to slide 20, you'll notice that in the bottom right, there's a hexagonal little structure there, okay? That's showing you the hexagonal unit cell. And you can see that there's this little kind of rhombus shape that's cut out of there. That's exactly the structure we were just looking at, that little kind of corner again on slide 20. And that is the unit cell of a hexagonal lattice. So the hexagon itself is not the unit cell, it's just that little sliver. Okay, so that's one interesting thing. So if we were to now take, back to slide 24, these 2-dimensional layers of hexagonal packing, which I'm trying to show you here. For example, here is one 2-dimensional layer of hexagonal packing. Of course, we'd repeat this over and over again, have a whole plane. We can now layer up these structures as we learned. We learned about the ABA structure and the ABC. So this is just A, and now B would fill in all the little points. So we'd put one here, we put one here, we put one here. The next layer would also be hexagonally packed, and we'd end up with an AB structure kind of no matter what. There's only one way to do that. If you then layer up a 3rd layer, so this is ABA, it's very hard to get this together without these magnets going everywhere, so I had to pre-prepare this. The bottom layer is very big, but maybe you can see, hold on. Maybe you can see, I have it barely, okay. I think you get the idea. Maybe you can see there's a hexagon on the bottom here. If you can't, sorry, I don't know how else to do this. Like this, there's the top hexagon. Then there's actually just a layer of about 3 in the middle, and then there's a hexagon with a whole bunch more on the bottom. I can try to take these off, see if this stays together here. You can kind of see that, right? Take these off. Oh, we're doing it. There we go. Okay, hexagon, then 3, then hexagon. Okay, this is ABA, and this is exactly, if you go back to the slides, what is shown on, again, slide 20, the unit cells. You can see how this hexagon might kind of slide over this, but again, the unit cell is just that little sliver of the hexagonal packing. Okay, if we now jump to, let's find this, slide 33, that's showing you the hexagonal closed packing. This is exactly what this is. Okay, we built this up by this kind of 636 type of geometry, and if you go to slide 35, in the bottom right, it's kind of like what I have here in the bottom right. There's a 363, but again, this is 636. It'd be harder for me to maybe make the other one. I can try. Let me try. Okay, but I could do the 363, and you can see that the planes of hexagonal packing stack up to a 3-dimensional hexagonal packing structure. So that should be kind of clear now, the hexagonal story. Now, we didn't cover this in any great detail in the class. And we didn't even cover any other structures that look like this. I'm trying to get this here. There we go. Okay, so this one is the one on slide 35 in the bottom right, where it's 363. Okay, and it's just packed up. So what we did is we then went to these cubic structures, and we talked a lot about cubic structures. But remember, these atoms want to pack hexagonally in 2D. Again, going back to slide 24. They really want to pack hexagonally. So what if we now start packing hexagonally, again, this AB structure, but instead of AB, we do ABC, okay? Which we learned about. If you just move one of the atoms in the third plane, it goes ABC, and that was shown on slide 36. We can get the hexagonal closed pack by doing ABA, and if we were to move that A atom over 1, we get ABC. That's the cubic closed pack. But remember, we're packing two-dimensional structures that are hexagonal, but when we pack them up, we claim we get a cubic. That should be very weird to you. Let me come back so you can see me, right? Well, you can probably already see me, so I can see myself. That should be odd, right? Hexagon, 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 and that's a cube? How does that happen? And so this is what I want to show you, and this is kind of the power of office hours. What we did is we went back to slide 34, the cubic closed packing, and there they actually tell you how to make this cubic structure from hexagons. They say on slide 34, you pack 1 is A, then B is 6 has a triangle kind of one way, C is a triangle the other way, and then there's another 1 for A. So you need 4 layers to show this cube. So what I've done here now is I've put together the 2 triangles, again on slide 34. Here's one of them, okay, and it's exactly kind of opposite this other one down here. So these are 2 layers. The layer would go on forever, but to show you this, I just want to put them this way. Okay, here's what, oops. Here's what one of the little triangles looks like. Okay, there we go. Just one layer, okay? But if I take this now, and I just put 2 more on it, watch this. I take this, okay, and I just put 1, I think it's right here. Yep. One right there, just 1 right on top. That's the new one I added. And I put 1 right on the bottom as another layer. This is hard to see. I put it right below that one, right here. Is that right? Yeah. Okay, I got it. Okay. What I've done is now I just have 4 layers. Now that's probably very weird for you to follow, but I think you understand. I had 2 layers with little triangles. Now I just added 1 to the top and 1 to the bottom, right on top of each other, right here, these 2. Okay. There's essentially 4 layers. If you turn this around and you look this way, right? That looks kind of like face-centered, one side of a face-centered cubic. If I go this way, there's another one. If I go this way, there's another one. This way, there's one. There's one over there. There's one on the bottom. I mean, this, remember I made this by stacking up 2 triangles and then 1 more on top. These are the 2 that were on top. Okay? I ended up making the face-centered cubic. Oh my goodness. So anyway, it's kind of ruined now. Okay, I had it, and hopefully you saw it. If you didn't, just rewind the video, because this is amazing, right? This is completely amazing. There it is again. Okay, so again, if you go back to the slides, you can see that's what we're trying to show on slide 34, and that's shown. That's what I was trying to show on slide 35. Okay, so 35, I was saying in the upper left, you can start the other way. Take the CCP lattice, double it. You can see that each of these atoms has a coordination number of 12. And then I was trying to show you these weird planes. So those 6 purple dots go around. That's one plane. Then there's this triangle on top, triangle on the bottom. Those are the directions of the planes that are hexagonally packed. Okay, and if you put this together right, you only need 1 atom from one plane, then 6 atoms in one, and you can make one of these unit cells. Completely mind-blowing. So now if you take this cell and you start looking between the atoms. Now this is really hard. You might have to come to office hours. Let me try this here. Let me try it again. Let's start over. But if you look between these layers, let's put this here. Here we go. This is the 2 triangles again. 1 here. Oops. That. There we go. 2 triangles. Yep. 1 there. See, these are really kind of a pain in the neck, these little toys here, especially when you fly them all the way to Mexico. There we go. Okay. And you put 1 here. Okay, now I might have to stop the video. I'm losing it, folks. Just hold on. This is good. Here. There we go. Okay. You can look down in here and you can see different holes. It's hard to see, but let me come back so I can see what I'm doing here. Okay. if you look in this face and you look between this one on this face here, and this one on this face here in this corner. Let me just angle it. Okay. What I'm trying to show you is that's tetrahedral. This one, this one, this one, this one. Let me kind of get it to you here. Right there. Right there. Oh, yeah. These two, the one that my thumb is on up top, and the one coming right out at you. That's tetrahedral. So behind that, there's what's called a tetrahedral hole. There's a little hole in the lattice where if you have an ionic compound and some of the radii are big, these are big radii, atoms with big radii, but right in that little hole, there's a little tiny one. And when something's positively charged, it tends to have a very small radius. You can squeeze it in there. So again, there's one tetrahedral hole, and that was just taking this face-centered atom and this corner. You can make one tetrahedral hole. If you go to this face-centered and this atom, there's another one behind there, another one behind there, another one behind there. So there are 4 tetrahedral holes behind this face, and then on the other side, you can do the same thing. This is falling apart, but there are 4 tetrahedral holes here. That's why there are 8 tetrahedral holes in this face-centered cubic lattice that came by us packing hexagonally in 2 dimensions. Okay, that's where those 8 little tetrahedral holes come from. So let me come here and see where we talked about that. I don't see it actually. I mean, I do see. I showed you some animations. I don't see where we actually define that there were that many. But there are, right? There's these 8 tetrahedral holes. I guess on slide 40 where we talked about alloys, there are 2 tetrahedral holes per each atom in the closed packed lattice, right? How many atoms are in this closed packed lattice? Each corner is 1/8 of an atom in the unit cell. There are 8 corners, so that's 1 atom. Each face is half of an atom, and remember from a die, a normal dice, a die, has 6 faces, and if each of them have half an atom, then there are 3 atoms due to the faces, 1 due to the corners. That's 4 atoms. So on this slide 40, we said there are 2 tetrahedral holes per each atom. So that means there are 8 tetrahedral holes, and I just told you where they are. Okay, they're behind this one in this corner, this one, and this one. And then the same thing on the other side. You can't see that. Okay, here. Behind this one, there's one. Let's see. This one with this one, and this one. That one. Behind there, there's 4. That makes the corner. Okay, then same behind there, and same thing on the other side. So that makes that, and then there's 1 octahedral hole per each closed packed lattice. That's harder to see unless you now go to these ionic crystals. So the ionic crystal section told us how these different shapes will form. The simple rock salt one on slide 42, if you click the link, you can see this sodium chloride lattice. Okay, now chloride being negatively charged has these more diffuse orbitals. So if you go to the website link I showed you, when you click on CCP, it will show you this cell. It looks like 8 unit cells, but it's only actually 1. All those corners should be the purple dots should be the chlorides. Okay, and now you can see the octahedral holes just go kind of in every other spot. So you can probably see from this picture the body center and then all of the other kind of edge shared atoms are the sodiums, and there are equal number of sodiums and chlorides. So there are 8 octahedral holes when you have this closed packed lattice for the 4 octahedral holes per the 4 atoms in the closed pack cell. Anyway, they're there in a 1-to-1 ratio. You can also see because of the body-centered nature of, again, for example, the 1 sodium, or the green atom, which I'm calling a sodium, this is symmetric, so it doesn't really matter, is bonded to 6 other atoms, the purple atoms, those are the chlorides. That's why this is a 6-6 coordination. Each sodium is bound to 6 chloride, each chloride to 6 sodium, because this is a symmetric unit cell. Let's keep going here. I actually have to be at a talk in 4 minutes, so I might go over. Then we talked about ionic crystals, and we didn't do this in any great detail, but what I said, it said on here, rock salt has this ratio of about 1/2. So that means that the sodiums, when the sodiums are half the size of the chlorides, you'll form that 6-6 octahedral structure. Okay, you'll fill in the octahedral holes. What typically happens, because it just, again, maximizes the intermolecular bonding and the strength of the bonding, is when the atoms are nearly the same size. For example, cesium chloride, again on slide 44, has this value for the radius ratio of 0.92. It's about 1, right? They about have the same radius. When that happens, you can't fit the cesiums in the holes because they're too big. Okay, remember, these holes aren't all that big. I gotta show it to you. They're not that big to squeeze a little atom in that little tetrahedral site in there. So if they're roughly the same ionic radius, you're not going to do that. The only place to put the chlorides, or the cesiums, excuse me, is in the very center of the body. And we know in body-centered geometry, the coordination number is 8. We learned that. And since this repeats over and over again, this is an 8-8 structure, the cesium chloride. 8 bonds from chlorides to cesiums and 8 bonds from cesiums to chloride, for each cesium to a chloride. At the bottom there, I listed other structures that have this radius ratio bigger than 0.7, and these have different coordinations, the fluoride, anti-fluoride, and the very big one. Let's just go and look at the fluoride very quickly, the calcium fluoride. Now, this is interesting. You might say, well, all the other stoichiometries you've had have been 1-to-1. Cesium chloride, 1-to-1. Sodium chloride, 1-to-1. Why is that? Well, it's because this big blobby crystal thing better be neutrally charged. If it's not, you have a charged crystal. This could be net negative, and that's not going to exist. That's going to attract to something else, right? You won't be able to put this in a beaker. So if I had now calcium fluoride, calcium wants to be ionically a 2+, fluoride wants to be a 1-, so it fills up its valence shell of electrons. So calcium 2+, fluoride 1+, you better have 2 fluorides for every calcium, or your structure won't be charged neutrally. Okay, and that's what you have, right? 1 calcium and 2 fluorides, CaF2. So it says here on the website that the calcium fills the CCP lattice. That's all the corners, right? And the faces, we know that has 4 atoms. So that means the fluoride, because there are 2 fluorides for every calcium, must fill 8 spots. Do we know 8 spots in a lattice that could be filled? Right? Again, that radius ratio is not huge. Okay, it's not close to 1, but it's bigger than 0.7. There's not going to be a lot of room. But if you expand these tetrahedra a little bit, if you pull this, let me see myself. Hold on. If you pull this one out a little bit, you could fit in there one of the other atoms, and that's exactly what happens. So in the calcium fluoride, if you're looking at the website, all of the tetrahedral holes, which we figured out there were 8, are now filled with fluorides. So the ratio is 1 calcium per every 2 fluorides, because there are 4 calciums in the cubic closed pack arrangement, which is face-centered cubic unit cell. Okay, there are 4 atoms in that unit cell, and thus we can, since there are 8 tetrahedral holes, we can fit in 8 atoms, and that's where the 8 fluorides go. Now, I think anti-fluorite was the other link we had. Yeah, sodium 2, oxygen. You always list the cation before the anion. That's why that's AB2, whereas calcium fluoride was, A2B, where calcium fluoride was AB2. It's cation, then anion. Sodium wants to be 1+, oxygen wants to be 2-, so now you need 2 sodiums for every oxygen, and the coordinations just flip. Okay, so now the lattice, instead of having the calciums at all of the corners, now we have the oxygens at the corners, and the sodiums, we need to have 8 sodiums. The oxygens are at all of the vertices of the unit cell and the faces. Then there are 4 oxygens per unit cell. Therefore, from the stoichiometry, we need 8 sodiums, and they're going to fill up all the tetrahedral holes. Easy. Okay? And so I think the last slide, and all I needed to say here, and the very last one, was this: when the radius ratio is less than 0.4, what happens? Okay, that's where one atom is much bigger than the other. Okay, when that happens, these little holes become a little larger. So in this case, the zinc sulfide, you can see automatically zinc wants to be a 2+, so that it has a filled d orbital worth of electrons. The sulfur wants to be 2-, so it fills up the p orbital. Zinc 2+, sulfur 2-, they're charge neutral. This is going to be a 1-to-1 stoichiometry. Okay, the bigger ones are the sulfurs, right? The negative charge is bigger. That's going to be at all of the corners. Okay, all the sulfurs will be at all of the corners. All of the lattice sites in the face-centered cubic, right? And since that results, all the sulfurs in the face-centered cubic vertices and faces results in there being 4 atoms of sulfur in the unit cell. Since this is 1-to-1, there must be 4 zincs. So where are the zincs going to go? Well, they could go into octahedral holes. That would make a 1-to-1 stoichiometry. But they tell us here when this radius ratio is less than 0.4, you typically don't get that. It opens up these tetrahedral holes, but you can't put the zincs in all the tetrahedral holes because there's 8 of them. Okay, and that wouldn't make the 4-to-8 stoichiometry, or that 4-to-8 stoichiometry wouldn't get you the 1-to-1 stoichiometry you know you need for zinc and sulfide. So the zinc only fill 4 of the tetrahedral holes, only half of them. Okay, and so you can go to the website again and look around, and you can now see that between these sulfur tetrahedral environments, there's a zinc right in the middle, and that's how you get the 1-to-1. So anyway, please rewind this video, go forward and backward, look at how I showed you how you take hexagonally packed 2D lattices, which kind of everything wants to be if it can, if there's enough space. And when you stack them up and you rotate it just right, you end up with this fantastic cubic geometry that we've talked so much about. So with that, I'm 3 minutes late to my the talk I'm supposed to be listening to. I'm going to say bye from Mexico. I will see you on Wednesday. I'm taking a really early morning flight on Wednesday, and I will quickly take an Uber down to Irvine from LAX. Hopefully get the class right on time to continue our talk on solutions. So read up on solutions. All right. Take care, everyone. Have a good President's Day. Bye.